Okay, good morning again. So we talked about the mini research, the tutorials that Engineer Jawad did, the mini research assignment. So you don't have to stick with these 10 sensors I mentioned here, okay? These are, I said, for example, it's just an example. So pick any 10 sensors that you would like to, okay? And we agreed that next Sunday, by next Sunday, you will already picked a project to do and communicated it to Engineer Jawad. طيب. Today, we're going to continue talking about interrupts. We started it last time. It is chapter 6 in the book. And we are going to go in detail. We're going to start picking them one by one. We're going to start with the external interrupt, and we'll do a hands-on example. Okay. So let me remind you what we did last time. Okay, how do I erase this? Okay. So if you remember, this is where we ended last time, before, and we talked about the concept of interrupts. It is recorded, and we talked about it even before back there a month or two ago in class. Okay, and we mentioned that the 16F84A microcontroller supports 4 types of interrupts: an external interrupt, timer overflow interrupt, port B interrupt on change, and E²Brown write complete interrupt. Okay, and we talked about each one of them. And we started looking at the interrupt structure. And we said that interrupts are 2 types: non-maskable interrupts that you as a embedded software engineer cannot disable them. So if they request to interrupt the CPU, then they will interrupt it. You cannot do anything to stop it. Interrupting the CPU means stopping the normal flow of the program counter in fetching and executing instructions, interrupting this normal flow. And the other type of interrupts were the maskable interrupts. The maskable interrupts are interrupts that you can mask, you can disable. And we have 2 levels of enable or disable for the interrupts. There is a global interrupt enable. This is a bit in a register, we'll see later. If you make it a 0, then you disabled the global interrupt. So 0 ANDed, if anything, will be 0, so nothing will interrupt the CPU. Okay, so if you want to disable all maskable interrupts, you just do this global enable bit, you clear it, without the need to go to each local enable for each of the 4 interrupts, or they're much more in other CPUs, other microcontrollers. Now for each individual interrupt, we have this structure: an interrupt source that comes from the hardware that supports that interrupt, that detects that the timer has overflowed or that the rising edge came on the pin, external interrupt pin, etc. It sets the output of this latch. So there is a flag that raises, becomes a 1, and this is also a bit in a register. And if the interrupt is locally enabled, this will propagate to, and if the global interrupt is 1, then we will interrupt the CPU. Okay. The CPU, once interrupted, the program counter will go and execute some code at the interrupt service routine. And when done, it will return from the interrupt back to where it was originally, the program counter. How does it know where it was before the interrupt? Well, when the interrupt happens, the structure also pushes the program counter to the stack So the return will pop or pull the program counter value from the stack and return it to the program counter, so it will go back to its main program where it was. Okay. However, if this interrupt flag is still 1, then the CPU could interpret this as a new interrupt came. It came again, and it will go back to the interrupt service routine. Then it will, when done, go back to the main loop, then interrupt service routine, and so on. This would cause the program to freeze or hang. You feel it's not responding. So it is important before returning from the interrupt to clear the flag, this flag. Okay, and I talked about it much more last time. You clear it by writing a message, a 1 here on the reset, so it will become a 0. We talked about it last time. You can go to the recording. The 4 types of interrupts, we talked about them in the 16F84A controller. Then when we move to the 16F877A controller later, in a later chapter, we're gonna find much more interrupts, okay? And we'll cover them as well. So for each one of the 4 interrupts, we have 2 things. We have an interrupt for each interrupt. We have an interrupt flag. 2, we have an interrupt enable bit. Okay, this is for each one. And we have a global enable for all of them together. So the structure would look like this. The logic that will send the signal to enter the CPU, which will trigger to push the program counter to the stack, load the program counter with a new value where the interrupt service routine is at, okay? There is a global interrupt enable bit. If it is 0, then whatever happens here, it's not going to interrupt the CPU. If it's 1, then interrupting the CPU will rely on this signal coming from here. This signal coming from here relies on any 2 bits related to an interrupt. So if you look at this one, for example, this is timer 0 interrupt flag. This is timer 0 interrupt enable. Okay, so in order for an interrupt to happen, you need first to enable the interrupts globally, then you enable the interrupt locally. Then if the timer 0 overflows and you enabled it, the flag will become a 1. So 1, 1, you enabled it. This the 1 will propagate until the CPU is interrupted. There's another logic here for the external interrupt. There is an interrupt flag for the external interrupt. There is an interrupt enable for the external interrupt. Same for port B change, flag enable, E square prom, flag enable. Any questions here? Is it clear? Okay, I hope it's clear. So these bits, let me clear the screen.
بس سؤال لو سمحت.
اتفضل.
هلا فوق هاي فوق الاند جيت الموجود الانتربت السي بي يو في هاي الويك اب اف ان سليب مود.
اوكي يس.
هاي مع التايمر اوفر فلو بتكون.
Exactly. Yes. So timer 0 لا مش تايمر مش wait a minute. Timer 0 will stop counting لما يكون بالsleep mode. Okay, it's not for timer 0. Okay, because timer 0 is a counter. It relies on the internal instruction clock. Okay, so it's not the only timer that can wake up the CPU from the sleep mode is the watchdog timer. Okay, not the timer 0, but the external interrupts could. The external interrupt and port B change will, if these interrupts happen, so if the arising edge comes on the pin of the external interrupt and you were in the sleep mode, the CPU will wake up. What does sleep mode mean? Sleep mode means that the main clock feeding the microcontroller is disconnected. So the program counter, the logic that has the program counter move from one instruction to another, fetch an instruction, decode it and execute it, this will stop. The program counter will stop moving. But you still have power to retain the data in the registers and the memory, but you will not be executing anything. But if an external interrupt happens, for example, on port B0, in this case, it's an external interrupt. Okay, if a rising edge is detected, the hardware would cause a wake up. A wake up means to connect back the clock. Okay, connect the clock and make the program counter go back to normal and start moving and fetching instructions. Okay. طيب. So these bits we talked about here, the enables, the flags 1, 2, 3, 4, 5, 6, 7, 8, 9. 8 of them are in one register, and the 9th is in some other register. There is a very important register called INTCON, Interrupt Configuration Register. Okay. And we will be dealing with this register a lot. زي كيف كنا نتعامل مع الستاتس register. Okay, port B register here. INTCON is one of the most important registers in this microcontroller. It's an 8-bit register. It is located in the data memory, in the RAM. Okay, and if you want to see it, it is, if I go to the data sheet, it is at location, what did I do? Yes. It is at memory location in the data memory, address 0B hex. See it? And it is in both banks, bank 0 and bank 1. So you can access it regardless of bit number 5 in the status register value. Okay? So this is the INTCON register. So the INTCON register is an 8-bit register starting with bit 0 up to bit 8. Bit 7, sorry, which is the 8th bit because we can't do it from 0, is the global interrupt enable. Okay? This is it, global interrupt enable. So here's the bit. If you want to disable global interrupts, you want to make this a 0 or a 1 by writing this bit, 0 or 1. See, here is it. Global interrupt enable, 0 means all interrupts are disabled, 1 means all interrupts are enabled. Okay? We said this is the global. For every other interrupt, we have an interrupt flag and an interrupt enable. So for port B change interrupt, there is a port B interrupt flag over here at bit 0 and port B interrupt at bit 3 enable. Okay, this is for port B change interrupt. And I'm talking about these two. Okay, interrupt flag, interrupt enable. These are the 2 bits. For the external interrupt, for these 2 bits, there is a flag and enable, and they are in the same register, flag, enable, interrupt, external interrupt flag, external interrupt enable. So we said, if you want to enable, so we're going to do after, shortly, we're going to do an example. We're going to enable interrupts, so we need to go make this global interrupt enable a 1 to enable all interrupts. Then we need to locally enable the external interrupt, so we make this bit a 1. Then, when a rising edge or a falling edge happens, this flag will raise. It will become a 1. So a flag is something you could read. By the way, if you did not enable the interrupt locally and an external, okay, but interrupts are enabled, okay, the flag may rise for timer 0, for example, okay, may rise, and you can go and keep waiting for it. Say while flag timer 0 interrupt flag equals 0, keep doing here something forever, else you can start moving. So you can wait. This is pulling again, okay? But it's not, the intention is to make it interrupt you, not just waste time. So the external interrupt enable and flag. Timer 0 interrupt flag, timer 0 interrupt enable. What's left? The E square prom. E square prom interrupt enable is here. The interrupt flag is in a different register, okay, for the E square prom. It is in a register called E square con 1, if you remember. We talked about it, I think, in chapter 2, okay? It's in a different register. Okay, so the endcon register is a core register. We will be using it a lot when dealing with interrupts. It's all about bits. Individually, you access them. For each interrupt source, there is a flag bit and an enable bit. And there is a global enable for all of them. Okay? As easy as that. So what happens when a CPU is interrupted, when this becomes a 1? If a flag is raised because the hardware detected that the cause of the interrupt has happened, and you already enabled it locally and globally, and 1 is set here to, excuse me, to interrupt the CPU, what happens? What actually happens? When this becomes a 1, a hardware detects it, okay? Originally, you are in the main program running. So our main program looks like this, right? So we have a while 1, right? This is our main loop, right? Doing this forever. Okay, and the program counter is just fetching instructions from here. It could be assembly or C, whatever. When an interrupt is detected, and underneath or above here, we have, and if we're doing C, we say interrupt. We write it like a function. But if we're doing assembly, we just write it at a label interrupt service routine, write any code, and then return from interrupt. Okay, but at origin 0x0004, you say go to interrupt service routine. Because when an interrupt happens, the program counter is pushed to the stack, okay, and loaded with address 04. So it goes to address 04. Then go to, it will find the instruction, go to somewhere. I tell it where is this somewhere, interrupt service routine, go to Ali to go to my interrupt 1, whatever. You execute some code you want to happen if an interrupt is detected, then you return from interrupt. Returning from interrupt will pull the program counter value from the top stack and return back where it was here. Okay, so if the interrupt is detected while an instruction is executed, in the middle of an instruction, it's not going to interrupt the execution of that instruction. It will complete it first. Okay, so complete the current instruction. Then the program counter, which points to the next instruction that is being executed and we just finished here, this value of the program counter will be pushed, saved to the stack. Okay, then clear global interrupt enable. This bit becomes a 0. What does this mean? It means that I disabled all interrupts, clearing the global interrupt enable, we disabled all interrupt sources, all maskable interrupts. Okay, so it is not allowed while you are here in the interrupt service routine executing any instruction in any code inside the program counter inside the interrupt service routine, it is not allowed for any other interrupt to interrupt you. So an interrupt cannot interrupt an interrupt, okay? Because we disable them. The hardware disables them. We don't do this. The hardware, once an interrupt is detected, the global interrupt enable becomes a 0 by default. In other microcontrollers, this is for the 16F84A microcontroller, okay? You may find in real life other microcontrollers that an interrupt can interrupt another interrupt with lower priority. So the term priority. In our microcontroller here, we have 4 sources of interrupts. They are all of equal priority, okay? Whatever happens first, it will take the CPU. And any other interrupt, if wants to interrupt the CPU, it will not be able to interrupt it if a current interrupt service routine is being executed, okay? So there are no priorities here. But in other microcontrollers, you may have this interrupt of a higher priority than this interrupt. So then if this interrupt service routine is executing, then this can interrupt it. But if the higher priority is executing, this cannot interrupt it, okay? A higher priority can interrupt a lower priority. Okay, so, but for our practice, this microcontroller, we don't have priorities. All interrupts are equal. So you disable interrupts globally, then no other interrupt can interrupt it. Well, let's assume that an external interrupt happens here. It will be detected, right? The flag raises. If you enabled globally and enabled locally, this will, what's here will happen, okay? We'll complete the instruction, push the program counter, disable interrupts. Well, after disabling interrupts, assume timer 0, if it is enabled, overflows. It wants to interrupt it will ask to interrupt it will ask to interrupt the CPU, okay? So its flag will raise, and you enabled it, but this global is 0, okay? So it cannot interrupt the CPU. But when you're done with your interrupt, this will become back as a 1, and these are still 1s, and so when you're done, the CPU will detect the other interrupt, okay? When you're done servicing the first interrupt, the CPU will go service the second interrupt immediately. Okay, so all interrupts are disabled. Then the program counter is loaded with address 04. Why 04? Because it is the interrupt vector, right? If we go to the data sheet, to the program memory, similar like, and we talked about this a lot, address 00 is the reset vector, which means we write our instruction, the instruction that we want to be executed when we power up our microcontroller or do a reset. In address 04, this is a reserved location. Here we write the first instruction in the interrupt service routine, okay? You can write your interrupt service routine here, first instruction, second instruction, third instruction. Oops, what happened? Okay, you can write them here, but you also can write them here at the end and have this first interrupt say go to where, to address 20, address 200, whatever, okay? So, but this 04 is fixed. And as I said in the past, for other controllers, it could be not fixed, okay? For every interrupt source, the hardware may send it to a different location, okay? But for our 16F84A, any interrupt happens, the program counter will go to address 04, okay? So how will you distinguish what got me to address 04? You will need to check the flag. If you're at address 04 and you have enabled multiple interrupts, how do you know that an external interrupt happened or port B change happened or timer 0 overflowed? You will need to check what which one of these flags is a 1, then you will service it. Well, if you found multiple ones, then it's up to you to say serve this one, then serve this one, or this one, then this one. Okay? If this flag is 1, do this, else if this one, do this. So in this way, you decided a priority that this will be dealt first if the flag is raised. طيب, so the program counter راح على average 04. راح يقول له where is the interrupt service routine? Go to the interrupt service routine. Then the program counter will continue execution. So address 04, fetch the first instruction at the 04, which is a go to, execute it, it will go to, then fetch the first instruction, the interrupt service routine, second instruction, third instruction. Okay, continue program execution. And every time when I fetch an instruction inside the interrupt service routine, I check if it is a return from interrupt. This instruction, we saw it when we learned about the instructions, return from interrupt. Is it a return from interrupt? No, then get the other instruction, execute it. Did we get to the return from interrupt? No, get the other instruction. Keep executing the interrupt service routine over here until we get to the return from interrupt. If we get to the return from interrupt, then we want to go back to our main program, okay? First, we set the global interrupt enable. So we enable the interrupts again to happen, okay? Then we load the program counter from the stack. Well, the stack, in the top of it, we have the previous program counter that we pushed to the stack when the interrupt happened. Now we load it back again we take it from the stack and send it to the program counter. Then the program counter will start fetching instructions in the main loop, okay? My taskbar is hiding, right? Continue program execution. Tamam? Continue program execution. And if you remember when we studied the returns, we had an instruction called return, right? This one, we use it with the subroutines, right? Subroutine. And we have this return from interrupt. And I asked you, what if you woke in the morning and you find that this return from interrupt enable is broken, or you're not allowed to use it, and you need to do interrupts? What would you do?
استخدم الرسالة العادية وبعدين
استخدم الريتيرن بس قبليها اكتب line of code to make this bit 1 صح؟ To make this bit 1. Set the global interrupt enable, then do a normal return. But if you do an interrupt return from interrupt, it will automatically embedded inside of it. It will set the interrupts, enable the interrupts again. So this is what happens when an interrupt is detected by the CPU. So this describes what we said when interrupt happens. This describes the flowchart. Should we start writing an interrupt, a program? And we come back to, these are examples, we'll come to them later. Examples in assembly and things. Let's do a practical program using interrupts. How about that? Maybe we're not going to finish it today, but let's start at least. So let's think of a program. So we want a program that has in its main loop something that is, when we usually do blinking, let's do something else. Something routine. Okay. Let's assume, you know what? Let me switch to my board. Okay. So, well, we can build on this or just make something new to learn new things. So how about we have port C, LEDs, like have one LED moving back and forth, back and forth. So this is on, then this is on, then this is on, and this turns off, and like an LED, so moving back and forth forever in the main loop. But when an interrupt happens, we go blink this 10 times, then we go back here. And the response has to be immediate. Okay, so let's do this program. Tamam. Okay, so if we want to do the software, we plan for our program, the software first. So this is what we want to do. We have a program, the microcontroller, 16F84A controller. We have port B, 2, 3, 4, 1, 2, 3, 4, and we have, this is 0, and this is port B7, and we have port C, 0, 1, 2, 3, 4, 5, 6, 7, okay, and we have an LED array here for all of them, okay, and I want one of them only on, and this moves back here, yani turns the first one for half a second, then turns it off, and turns this one for half a second, then turns it off, then this one for half a second, and so on, and then bounce back again, just like a bouncing ball. And whenever an external interrupt, and we want to do an external interrupt, and we know that external interrupt is shared with port B0 pin, right? And it happens on a falling edge or a rising edge, right? So if you go back to our sources of interrupts, external interrupt, this is the only external interrupt input. It shares a pin with port B0. It is edge triggered, okay? We can change the edge. What is the edge? A rising edge or a falling edge? Well, anyways, we need to do an edge. We need to do an edge. So we can do it this way. We can have a push button. A push button, just like last time, with a pull-up resistor to VCC and the ground here. So normally, the pin will be high, right? But when we push the button, the voltage on this pin will drop to low. So this is a falling edge. And if we release the button, it will go back to high. And this is a rising edge. So we can do this kind of interrupt, okay? So let's write our program. So we start a new project and choose where to save it. And again, remember, I upload all these demos to our class page. We call it class demo 6 external interrupt. Okay. Okay. 8 megahertz, nothing to import, finish. So this is our program. So let's try the skeleton, okay? Let's try the skeleton because it's 10:50. We're not going to be able to finish it today. We'll do it next time. But the skeleton will be, first, we can do this in the flowchart, right? Initialize all registers, the ports, right? For the ports. Then we need to enable the external interrupt, right? Both globally and locally, right? Then we start our infinite loop while one. We start doing whatever we want, do the LED shifting here. Oops. Do the LED shifting on port C, bouncing back and forth here forever. And when an interrupt happens, when a port a falling edge is detected, we go execute the code inside the interrupt service routine that we write over here. Okay, what we do, we will make, for example, blink port B 10 times. Then we will what? Clear the interrupt flag, because if we don't do that, every time our interrupt is done and we go back to our infinite loop main program, it will the flag is raised, the enable is there, external and global and local. Then it will go back here and blink port B 10 times, then come here, and so what you will see that your CPU or your microcontroller is stuck just blinking port B forever. Okay, that's why we need to clear the flag. So this is the skeleton of our program. We finish it next time, inshallah. Any questions?
دكتور سؤال.
Yes.
هلا اذا هون بالسي بدنا نكتب شيفت ليفت مثلا، كيف كنا نعمل شيفت ليفت؟
Okay, so انت مستعجل. Well, you can do it like this. Port C, shift left equals port C, shift left one time.
Okay.
One time. We'll do it next time. That's why I choose the shift. يعني it's يعني do يعني multiple things in hit two birds in a تعلم interrupts ونتعلم شوية skills أخرى بالسي or something. Siwar, you raised your hand.
دكتور بالغلط.
Okay. No more questions?
الله يعطيك العافية.
I'm gonna الله يعافيك. I'm gonna
يعطيك
stop
العافية.
the Let me stop the recording. Thank you very much. See you Tuesday.